All right, moving on with an application of vectors. We've covered all the nuts and bolts and operations of vectors. This application right here, where we're dealing with aviation, this is probably going to be the most cumbersome of the vector applications we'll do. Um, and a few notes when we're dealing with aviation, and this could also refer to boats, if we're having a boat somewhere fighting a ocean current or something like that. But the plane's direction is often indicated by a vector, and the velocity of an airplane corresponds to the magnitude of a vector. So if I tell you that a plane is traveling at 800 miles per hour, then that means the velocity or the magnitude of that vector would be 800. The heading or the bearing of the plane, it is an angle measured from due north going clockwise. So this is going to be kind of a different way of looking at angles, but when we're dealing with aviation, unlike the unit circle, which starts on the x-axis and opens up counterclockwise, aviation actually starts on the y-axis, which is due north, and we open this way. So if I wanted a bearing of 50 degrees, then that means I would start on the y-axis and then open counterclockwise or open clockwise 50 degrees. So that is what a 50-degree bearing would be like. And then finally, to find the effect of wind speed on a plane's direction, you find a vector for both of the plane and the wind, and then you add the two vectors together. Your answer, the resultant vector, is the plane's actual path as affected by the wind. So there's a few notes for you, and let's do two examples. First one's going to be pretty straightforward because I'm nice and I just straight up gave you the vectors for the plane and the wind. Sometimes I'll call wind a jet stream. It's kind of the same thing. So P for plane, W for wind, says find the plane's adjusted vector. The plane thinks it is going, see, I'm going to draw this out. The plane thinks he's going in the direction 0, 400, which 0, 400 means you are not moving left or right, and you're going straight up 400. So that's what the plane thinks it's doing. The wind, however, is going 10, negative 25. So my wind goes 10 right and down 25. So my wind is doing something like this. Well, if you can imagine, now my wind is way too long. My wind probably wouldn't be that long. My wind is actually going to be something like this. But if you can imagine, this plane is actually going to be slowed down some, and it's going to be pushed off its path a little bit because it's going almost against a headwind. So the wind will affect the flight of the plane, and that's what we have to figure out. The adjusted vector for the plane, you simply add those two vectors together. So P plus W is going to be 0 plus 10 and 400 plus a negative 25, which gives you a new vector of 10 and 375. And that is our plane's new vector. I'm going to call it N for new vector. Then it says find the plane's new velocity. Well, the velocity, I told you, is the same thing as the magnitude of the vector. So the new velocity is going to be the magnitude of that vector I just created, which would be the square root of, and you square each component, 10 squared plus 375 squared. And we'll throw that in the calculator. Let me do that real quick. There we go. I threw that in the calculator and I got 375.133, and my units for velocity was, oh, I didn't give it to you. I will say miles per hour. I will include enough information. So that's miles per hour. That is a horrible penmanship, but whatever. All right, so we throw that in and we get the new speed, which is 375. What is the new bearing of the plane? Now, the bearing is a little bit trickier. What I'm going to do to find my bearing, I know that my new vector for the plane is right 10 and up 375. So I'm going to sketch that real quick just because I'm very visual. I'm going to go right 10 and up 375. And it's not even going to be a very good graph. I know that my plane's new vector goes right some distance and then it goes up a whole lot. So it goes right 10 and up 375. And I'm going to create a right triangle, which we've done this before. I went right 10 and up 375. And what I'm going to do first is find this angle right here, because that's the angle that's in this triangle. And then I will use that. You know what? Yeah, I'll stick with this way. I will use that angle and then subtract it from 90 to get the actual bearing. I want that actual angle right there. Uh, well, if that's theta, tangent of theta, I have the opposite and the hypotenuse, and the adjacent. And so my angle theta is going to be the inverse tangent of 375 over 10. And I'll punch that in the calculator and get that answer real quick. All right, and when I punched that in, I got 88.472. But remember, when you do bearings, the bearing is measured to due north, which is the y-axis. So I will do 90 degrees minus that answer. So my bearing, or my heading, is going to be 90 degrees. That's a horrible 90 degrees. That's not much better, is it? Minus 88.472. I'm going to do this in my head, which is dangerous, but I think that's going to be 1.518 degrees. 1.518. So it actually wasn't pushed off too much. And this is not drawn to scale. Notice if I went over 10 and up 375, my vector that I actually drew right here would actually look more like this. It'd be way, way, way up here. And an angle of 1 degrees might be about reasonable. So there we go. Let's look at the next problem. The next problem is going to be a little bit, I'm not going to say a little bit, next problem is going to be a lot tougher because this one I didn't just straight up give you the vectors like I did on that last problem. In this case, I give you the velocity of the plane, and then I give you where it's going, traveling due east, and then I do the same thing for the wind. I give you the velocity, and then I gave you the bearing. Oh, never mind, that's right. I gave you the heading of 45 degrees and a velocity of 30 miles per hour. We have to take that information and get the vectors of the plane and the wind. So here's what I'm going to do. I know that my plane is 450 miles an hour traveling due east. Now, I do expect you to know your 4 basic directions. You have north, which goes up, south is down, east is to the right, and west is to the left. Now, if there was some geographer, he'd get mad at me for using the phrases up, down, left, and right, but that's good enough for me. So if I'm traveling 450 miles per hour, that's the magnitude of my plane. My magnitude is 450 miles an hour. Whoops, forgot the 5. So I know I'm going 400, the length is 450, and if I travel due east, well, that means my plane is going just straight to the east 450 units, right? I'm going straight east 450 units. So if I go straight east 450 units, that's to the right. So I know my vector for P is going to be to the right 450, and I'm not going up or down at all. So there's the vector for the plane. That one's not too bad. The wind, however, is a lot tougher because my wind is not going straight left or right or up or down. It's going at an angle, and that makes the wind a little bit trickier. My wind is going at a bearing or a heading of 45 degrees, which means the wind is coming off the north 45 degrees this way. That's where my wind is. So let me draw my wind vector. It's going off this way, and the magnitude of my wind is 30, because I said it's going 30 miles an hour. So I know the magnitude of my wind is 30, and I have a direction, a bearing of 45 degrees. I really wish I'd chosen 30 degrees, but we'll stick with 45. Hey, there is a way to write a vector. I told y'all this, I guess, last week at some point. If you have a direction angle and the magnitude, you could write a vector in this form. It's the magnitude of the vector times cosine of the direction angle, and then the magnitude of the vector times the sine of the direction angle. I also gave it to you. Let me see if it's all that grouped. Why does it do stupid stuff like that? Hang on just a sec. There. So I also gave you this one where it's the magnitude times cosine theta I plus sine theta j. I gave you both of those two forms for a vector if you knew the magnitude and you know the direction angle. Well, I know the magnitude, and the heading is 45 degrees. The direction angle, now this is where it's confusing, the direction angle right here This is your old school unit circle angle. Oh, I forgot the H. Yeah, old school unit circle angle. So if my bearing is 45 degrees, this one's going to be kind of nice, then the angle coming up this way, my direction angle, is also 45 degrees. Subtract from 90. And I know that my direction angle, theta, is 45. Then I could take that information, and I know that my wind's vector is going to be the magnitude times the cosine of the angle plus, not plus, comma, and then the magnitude times the sine of the angle. So 30 times sine of the angle. Good, 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 good. Then I will simply throw those in the calculator and get the vector in nice numbers instead of having cosine and sine. So let me punch that in real quick. There you go. So I punched that in. And when you punch it in the calculator, the TI-89 spits it out as 15 square root of 2 and 15 square root of 2. I actually am a fan of decimals for problems like this. So I'm going to write the wind, and I repunched this in to get a decimal. It's 21.213 for each component. Do make sure that your calculator is in degree mode for these problems. And I should have pointed that out on this last page. Notice when I punched in this one, my calculator is actually in radians, but down here I flipped it to degrees because I needed my angle in a nice recognizable form for the bearing. So make sure your calculator is in degrees for these. So now I have my vector for the plane and for the wind. That is the toughest part of these problems, getting the vector. Because once you have the vectors in component form, then to find the adjusted path, we simply add those two vectors together. The new vector for my plane is going to be the plane's vector, the original vector, plus the wind, which is 450 plus 21.213, and 0 plus 21.213, which gives you a vector of 471.213 and 21.213. Good, 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 good. So we have that new vector for the plane. And now the other two questions coming up on the next page are what is the plane's new velocity and what is the plane's new bearing? So I'm going to pull in my plane's new vector. Let's see, I don't need all of that. Let me do this. Copy that. Cut. I could have paused the recording while I did this. Couldn't have I? Nah, that'd be make too much sense. All right, so there's my plane's new vector. Velocity, once you have that new vector, velocity is simply the magnitude of that vector. So my velocity is going to be the square root of 471.213 squared plus 21.213 squared. And it's going to be an ugly number because you have all these crazy decimals. You're squaring it, then you're going to take the square root. But this is what calculators are for. So let me punch this in. And you get a new velocity of 471.690. And this problem, I did give you units this time. It's miles per hour. And always be aware of whether or not the answer makes sense. Let's go back and look at what's actually happening here. I drew these vectors. My plane is traveling to the right, and the wind is blowing to the northeast. So if my plane's traveling to the right and the wind's blowing to the northeast, the wind's kind of behind the plane, so it's going to speed it up a little bit. I was at 450, so a new speed of 471 makes sense because my wind is coming from behind the plane and hitting the rear end of the plane. Then finally, the plane's new bearing. I'm going to do the same thing. My plane, the same thing I did on the last problem, I'm going to sketch it very roughly. My plane's new vector is to the right 471 and then up 21. So I'm going to go to the right 471 and then up 21. And so here's where my triangle is, 471 up 21. And then I'll use tangent to get this angle. So this is 21.213, 471.213. I'm going to find this angle, and then I can subtract from 180 to find the actual bearing right here. So theta, the tangent of theta is opposite over adjacent, 21.213 over 471.213. Let me punch that in real quick. And when you punch this in, if you think about this angle, if we go right 471 and then up 21, I should get a really small answer there. And the answer that I ended up getting was 2.578. Where is it? Oh, there it is. So I get an answer of 2.578, which that's reasonable. That's reasonable. So 2.578. Just remember, that's not the bearing. The bearing is measured to due north. So my bearing, I will simply subtract that from 90 degrees. So my bearing is going to be 90 degrees minus that answer, 2.578, which would give me, what's that, 97.422 degrees would be the bearing. So there we are. Two problems. The hardest part is getting these vectors right here. So there you go. We'll polish this out later.